In this video, we're going to continue going over the topics of chapter 6. Now we're going to proceed to learn how to name aldehydes. When it comes to aldehydes, we need to find the longest carbon chain that contains the CHO group. The CHO group is going to be where carbon is double bonded with oxygen and to one side of the molecule is bonded to hydrogen. Then we can write the alkane name for this parent chain, and we replace the E ending with the ending AL. So all our aldehydes are going to finish in AL when we name them. When it comes to numbering, we are going to number the carbon chain starting from the end that starts where the carbonyl is. So remember that the carbonyl group out of this C double bond OH is specifically this area. Because in aldehydes, the carbonyl group for at least straight chain aldehydes is always going to be carbon 1, we can omit the number 1 when we're naming aldehydes from the parent chain. Then we have to give the location and the name of the substituents as a prefix of the name of the aldehyde parent chain. And remember that if we have location and words, we utilize a hyphen in order to separate them. Remember that the rules are outlined specifically on chapter 4 of our textbook. So let's go over the 2 examples that we have right here on the slides. The first example that we have, I want you to take a moment and find the longest carbon chain in this straight chain aldehyde. When we try to find the longest carbon chain, starting from the carbon in the carbonyl, we find that there's 1, 2, 3, 4, 5, and 6. So if we are trying to determine the alkane name for a 6 carbon parent chain, that's going to be hexane. But because this molecule is an aldehyde, we are going to erase the E and we put an AL ending to our molecule. As the instructions showed, when we are numbering our aldehyde and we have a straight chain aldehyde, carbon number 1 is the carbon in the carbonyl, and then we proceed to number the parent chain. So this is carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. We can observe that here we have 2 substituents that are the same on carbons 3 and 4. In this situation, we can observe that these substituents are methyl groups because we have CH3s. So we're going to put methyl as the name of the substituent. We're going to put di because there's 2 of the same, and then we're going to proceed to put their location, 3, 4. So the name of this aldehyde is 3, 4 dimethyl hexanal. Aldehydes can be aromatic, meaning that the aldehyde motif, that CHO group, which is this area, Let me highlight it. Can be attached to an arene. When that happens, the whole motif of the CHO group attached to the benzene becomes the parent chain, okay? That group that I actually highlighted in red, it is known as benzaldehyde. When benzaldehyde is our parent chain, we are not going to number the carbon atoms starting from the carbon in the CHO group. We're going to do it from the carbon atom in the benzene ring that is holding the CHO group. So what that means is that when I'm numbering the carbon atoms in my benzaldehyde, this is carbon number 1. Similar to the rules for cyclic alcohols that we observed in the previous video, we can number the rest of the substituents that are present in my molecule clockwise or counterclockwise that they have the lowest number. In this example, we have to go counterclockwise. So this represents position 2, position 3, position 4, position 5, position 6. So in this benzaldehyde, we have one substituent, which is a CH2, CH3 group. That is known as an ethyl group. And its position is going to be position 3 in the benzene ring away from the carbon that is holding the CHO group. The next functional group that we're going to learn how to name is going to be ketones. When it comes to a ketone, similar to what we have observed through our discussion of organic chemistry in chapter 4 and now, we are going to find the longest continuous chain of carbon. We're going to write the alkane name, but if we have a ketone, then understand that the ending is going to be -one. And we do that by replacing the E in the alkane name with ONE. We're going to number the carbon chain starting from the end that is nearest to the carbonyl group, meaning that C double bond O group in our ketone. We have to give the location of which carbon is holding that double bond to oxygen. We also have to give the location of any substituent if it's present. And remember that if we give location and words, we are going to separate them by a hyphen. If you need to review, as I have mentioned throughout, how to name substituents, remember to refer to chapter 4 for that information. So let's actually go over the following examples that we have on the slides. Here we have a straight chain ketone. We have to take a moment and find the longest carbon chain in this molecule. As you can see, in this molecule, my longest carbon chain is going to be 1, 2, 3, 4, 5 carbons in length. The alkane name for 5 carbons in a row is going to be pentane. But because it's a ketone, we're going to erase the E and place ONE as my ending. So the parent chain is now called pentanone. When we are numbering our carbons, we're going to do it from the end that is closest to the C double bond O, remember that that is called a carbonyl group. This is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5. We can observe that our C double bond O is on carbon 2. And whenever you have a ketone that has 5 carbons or more, you have to get the location of the double bond oxygen. Next, we are going to name the substituents, if any. In this molecule, we have one substituent. We can see that that substituent specifically is a CH3 group. That CH3 group is known as a methyl group. And that methyl group is on position 4. So the name of this molecule is 4-methyl-2-pentanone. Ketones can also be cyclic. So let's do an example like that. So here we have a cyclic ketone. Take a moment and write down what is the name of the cyclic ketone if it didn't have any substituents, based on the rules that you have learned already how to name these functional groups. So for the ketone, overall, we can see that there are 1, 2, 3, 4, 5, 6 carbons. That means that that cyclic system will be known as cyclohexane. If it was an alkane, but because this is a ketone, this is cyclohexanone. When we number a cyclic ketone, carbon number 1 is going to be the carbon that is holding the double bond oxygen. So this is carbon 1. Next, we have to number our molecules clockwise or counterclockwise to determine the positions of the substituents present and give them the lowest number. So for this molecule, we have to go 1, 2, 3, 4, 5, 6. In this cyclohexanone, we have 2 substituents. At position 2, we have a methyl. At position 4, we have an ethyl group. Lastly, when we are writing the name of our molecule, let's understand that the substituents needs to be written in alphabetical order. So when it comes to this, let me make this a little bit larger. Let me move it to the side. In order to correctly place the names of the substituents, the ones that comes as the second word is going to be the methyl group, which is in position 2. And before that, we have to put the ethyl group, which is on position 4, because we need to place them in alphabetical order. Now let's focus on the different types of monosaccharides when we are starting our discussions on carbohydrates. So monosaccharides can actually be categorized by 2 things. Number 1, the number of carbons present in the structure. If we classify our monosaccharides by the number of carbons in the structure, then understand that we can utilize the following terms. The smallest carbohydrate is going to have 3 carbons, and the largest monosaccharide, I should say, is going to have 8 carbon atoms. So if we are going to classify them by the number of carbons, these are the terms that we utilize. If your monosaccharide has 3 carbons, then that is known as a triose. If your monosaccharide has 4 carbons, that is known as a tetrose. If your monosaccharide has 5 carbon atoms, it's known as a pentose. If your monosaccharide has 6 carbon atoms, it's known as a hexose. Based on your knowledge of prefixes, try to predict what would be the numbers, or the names, I should say, for monosaccharides that have 7 carbon atoms and 8 carbon atoms. For 7 carbon atoms, the name will be heptose. And for 8 carbon atoms, it is octose. As you can observe, carbohydrates, their name is going to end in OSE, as you can see from the different words that we utilize to describe the number of carbons present in a carbohydrate. The other way that we can classify carbohydrates is depending on the carbonyl functional group that they have. If the carbohydrate has an aldehyde group in its structure, it is known as an aldose. If your monosaccharide or carbohydrate in general has a ketone group in its structure, is known as a ketose. So here we have examples of 2 different monosaccharides. We can see erythrose on the left, which has a aldehyde functionality. So that is known as an aldose. And because of its number of carbons, predict what will be the classification of it. This molecule, it is a tetrose because it has 1, 2, 3, 4 carbon atoms. On the right side, we also have erythrulose. Erythrulose is also a tetrose, but this tetrose, because it has a ketone, and we can see carbon chain, carbonyl, carbon chain, that ketone motif makes erythrulose a ketose sugar. We can see the examples here of glucose and fructose. These are 2 monosaccharides that, based on the name, we can determine the functional groups that they have. When we combine the classification of carbonyl functional group and number of carbons, let's notice that the word aldose the SE is omitted, and that is put together with the carbon classification. That's why we see that glucose is an aldose sugar, because it has an aldehyde, and it is a hexose sugar because it has 1, 2, 3, 4, 5, 6 carbon atoms. Fructose, we can see that similarly, the word ketose loses the SE, then is combined with the carbon classification of this monosaccharide. So fructose, because it has also 6 carbon atoms, it is another hexose. 1, 2, 3, 4, 5, 6 carbons. Now the difference is that it is a ketose sugar because it has this ketone functional group in this area of the molecule. Let's actually practice classifying carbohydrates. Let's classify the following monosaccharide. We can observe that some carbons are not written but implied because the body of our monosaccharide is given in skeletal form. So take a moment, write the molecule, determine how many carbon atoms are present. In this molecule, we have 1, 2, 3, 4 carbon atoms right here. But overall, in our molecule, we can observe that we have 1 carbon atom, 2, 3, 4, 5, 6 carbons. Since our molecule overall has 6 carbons, then this molecule is known as a hexose. Additionally, when we look at the functional groups that are present in the molecule, we can observe that we have a carbon chain connected to a carbonyl, connected to another carbon. That means that we have a ketone functionality. So that portion of the molecule, we will say, oh, it is a ketose monosaccharide. But when we're trying to incorporate carbonyl functional group in number of carbons, we are going to omit the SE ending. And we're just going to place the letters K, E, T, O next to the number of carbons. So as you can see, this is a keto hexose. Predict the classification of the following monosaccharide.